Hello everyone, let's continue with the example. So we have assumed that we have an array M of 3 double words. So let's try to understand what are we trying to do here. What we need at the end is we want to store or we want to load this particular content into one of the register, let's say X8. So that's the final aim that we need to do. So let's try to understand how do we do it. So let's say we have some examples over here. X8 is the register inside which we want to load this particular data. And if you want to access this data from the memory, you need the first address of that particular memory, because if you want to reach to a point called the 16th bit of this particular memory, you need to get the first address in order to access the 16th address of the memory. So in that case, we'll store the x23, we'll store the base address of this entire memory into a register called as x23. Let's say we'll keep it very simple. X23 will contain the base address as 0. So let's say this particular memory will start at 0th location. Next, what we have to do is now we have to find out a way to load this particular content inside the register X8, and the command that will, the RISC-V ISA command that will be helping you to do that will be LD. So LD is nothing but the load double word. So LD is nothing but load double word. X8 is the destination register where you want to load your data. And x23 and the offset is basically forms this particular entire thing forms your source address. Basically offset immediate is 16 and x23 is the source register RS1. So the way it works is 16 gets added to the contents of x23 to form the final address. Now contents of x23 is 0. You add 16 to it and the pointer reaches at this point of time. And as a result of that, now in this particular command, this is since the command says it is load double word, it will start loading from this point into the register the way it was loaded inside the memory. It's a little indent memory system. So this one, the lowest bit will come over here, which is the lowest bit of the X8 register. The next byte, the next 8 bytes or 8 bits or the single byte will come next to the first byte, which is over here. So it's basically the little indent memory system that we have seen some time back. Let's look into how is this particular command is being represented inside a computer. So this is how it will look like. So you have this, all the instructions in the RISC-V are generally 32 bits. I'll tell you, we'll talk a lot about the size of the instruction set once we reach there. But first of all, let us try to understand the size of the instructions. All the instruction sizes are 32 bits. Though it is called a 64-bit, this is 64-bit for the registers, but the instruction size for 64-bit and 32-bit RV or RISC-V will be all 32 bits. So the first, from the 0 to 7 bit, the 7 bits are used to 0 to 6. The 7 bits are used to represent this particular command called as LD, which is load double word. So along with this particular 7 bits, you need the func3 also. So these are additional opcode bits. So along with using a combination of func3 and the opcode bits, so you will get to know the final keyword or final opcode that you want to load, or final command or the instruction that you want to use. So this 7 bits and this 3 bits forms the opcode of the load double word. Opcode is nothing but a code which will instruct the computer to use load double word command. That's the opcode. And your RS1 is the source register, which is 23. So there will be it's a 5 bit. 5 bits are used to represent RS1. So based on the combinations of the 5 bits, you will get the value 23 over here. 23 will be loaded over here, and RD will be 8. So since the destination register is X8, the value of this particular RD will be 8. The way 8 will be represented over here is 0 1 0 0 0. So that represents the binary pattern 0 1 0 0 0 will represent a decimal value of 8. So that is the way it is being instructed to the computer to do a load double word using the bit pattern which is present over here. So this command will be represented in the form of 32-bit pattern. And the 16 number that you see as an offset, it will be represented using the next 11 bits or the next 12 bits from 20 to 31. This is how we will represent the immediate number. Okay, so that was about one of the commands. Let's take a look into another command. So for example, now if you want to add the contents of this particular double, or if you want to add the double word to some of the contents of x24, all we need to do is add X8 and add x24 and X8 and store the result into add. So this becomes your destination register. This becomes your RS1 and RS2. So let's look into that. So this becomes the add command. This becomes your destination register where you want to load the output of x24 plus X8. This becomes your source register RS1, and this becomes your another source register RS2. The way you want to represent, or way we instruct the computer to do the add command is something like this. Again, the 7 bits are used for opcode. A combination of 7 bits plus func3 plus func7 forms the real opcode of the add instruction. RD represents the destination register, which is X8. RS1 represents X24 and RS2 represents 8. Similarly, since there is a 5-bit pattern over here, the 5 bits will be used to represents X8. This 5 bits will be used to represent 24. And this 5 bits will be used to represent 8. Again, let's take a look into another command. So for example, if you want to store the result, whatever result you see and the X8, you want to store it back to the memory. Now in the memory, the locations from 16 to 23 are already occupied. So let's try to store it in the memory location which is free for us. So for example, let's say we want to store this particular content of X8 into the memory starting from location 8 to 15. In that case, we need to do something else. The command to store the data from the register back to the memory is something like this. And we need to do this because we have got a very limited amount of registers available with us. And as a result of that, these registers might get occupied very fast if we don't store the contents of the register back to the memory. So that's why we need to load and store. We need to do operations on the registers, but we need where we can store enough amount of data. Okay, so the command is store X8 from X8 to X23. X23 is the register which holds the base address of 0, and 8 is the immediate offset. So it basically calculates it adds up 8 to the contents of X23 and reaches the value of 8. So now currently the memory pointer is that value of 8. So this pointer will be pointed over here, and the command to store the double word back to the memory is SD. SD is nothing but the store double word command. X8 is your data register. Now why we call it as a data register? Because this is the one that holds the data, that holds the 64-bit data. And then you have the source register RS1 and the immediate value and the immediate value 8, which needs to be added to the contents of X23. Now similarly, the way we want to represent or way we need to instruct the computer to do this particular command is something like this. Again, the first 7 bits will be opcode, and the first 7 bits and this func3 will represent the opcode. So there is a way you use a combination of this these 7 bits and these 3 bits to form the opcode for store double word. Then the immediate value, which is 8, is been split around between the first 5 bits are represented over here, and the remaining 5 to 11 bits are represented over here. So it gets split over here. Now over here, if you see, if you want to represent 8, the 8 is basically 1000. So the lower 5 bits will settle over here, and the upper 5 bits which will be all zeros will settle over here. And finally, you have the data register RS2, which is being used to where we have 5 bits to represent the data register RS2. We have 5 bits to represent the source register RS1, and the 8 is settled over here. So what we'll do is now from these three points we need to conclude a couple of things. So what we'll do is we'll stop at this point and we'll start to conclude certain things from the output of these instructions and the instructions that is being stored in the computer memory. So let's try to stop at this one and let's start from that point from the next video. Thank you.